All right, well, greetings everybody. We're ready to start the webinar. I have straight up 12 o'clock or the top of the hour, 12 o'clock Central Time anyway. Um, we'll go ahead and get started. I know a number of people are going to continue to log in, but that's fine. And we have some introductory remarks here to make to start. I am Greg Freeby, the Executive Director of the American Segmental Bridge Institute. Looking forward to hosting this webinar for you today. You can see my contact information on screen should you need to get in touch with me at any time during the presentation or afterwards. And there's other means you can contact me during the presentation, and we'll cover that in just a minute. You should have logged in expecting to see a presentation today on what have we learned from 10 years of data on the new I-35 St. Anthony Falls Bridge in Minnesota. If that's not why you logged in, then you'll be pleasantly surprised perhaps, because that is the topic we're covering today. So some brief announcements before we get into some of the mechanics of the webinar, and then also some details about upcoming events. So upcoming events, ASBI is hosting our annual grouting certification training, again by webinar this year on April 12th. That's just a couple weeks away. That's a Monday from 8 o'clock to about 5:30 Central Time, depending on how long it takes you as an attendee to complete the exam. You can check the website for details on the training. Registration is open on the website. You can register entirely through the website. A reminder, there is a fee associated with this training unless you are DOT staff, and in which case the registration fee is waived, and you'll find that information online as well. But again, if you need to contact me regarding that training, you're welcome to. Today is our first of a series of webinars that ASBI is going to be conducting this year. Just to try to get sort of the date in your head, the plan is we will have a webinar the last Wednesday of every month. So each month you'll see a new webinar. We're trying to be a couple months ahead of them in terms of having them planned. So next month's webinar at the end of April on the 28th is Mr. Brian Merrill is going to be talking to us about how the first segmental bridge in the U.S. is performing, the JFK Causeway. His firm, West Genie Elsner, did a very in-depth evaluation of that structure for the Texas Department of Transportation. And he has some really interesting information about the construction of that bridge and then its overall performance. It's closing in on 50 years old, and 1973 is when it opened to traffic. So it's almost 50 years old. So there's a lot of really interesting information in that presentation about the performance of that structure. You can register for that on our website as well. If you go to the events tab on the ASBI website, you'll find you can register for that webinar. And then we'll have announcements coming out very soon about upcoming webinars in May and June. We'll continue the cadence throughout the rest of the year. The 1 month we won't have a webinar will be in November, because in November we will be hosting our 2021 annual convention in person at the Westin La Paloma Resort and Spa in Tucson, Arizona. The hotel is it has assured us that they can meet and accommodate any social distancing or COVID requirements we have during the event. We certainly we're gonna follow not only the state of Arizona and the CDC recommendations, but we're likely to amp it up a little bit more and insist on doing some things to ensure that all of our attendees remain safe from COVID. We have the ability at this facility to really spread out. Social distancing will be very easy to accomplish. So some elements of the convention may also be available in a hybrid fashion for those who are unable to attend, but certainly we encourage everybody who's able to attend in person to please do so. So some quick instructions about our webinar today. The first is if you logged in to the call today or the webinar today using your phone, you do need to log in with computer audio. So if you've connected to audio by phone, I encourage you to log out and log back in using your computer audio with speakers or an earbud or whatever. We're using a pre-recorded presentation, and you won't be able to hear the audio from that presentation if you don't log in with computer audio. We are offering professional development hours for participation today. We understand that because it's a webinar, at times you might lose your connection. If you do lose your connection, you can log back in. We will be issuing certificates, but only to those who meet the minimum attendance requirements in order for the session. So if you do lose power, don't freak out. It doesn't mean you're not going to be able to get credit for the session. You'll just need to get logged back in and not miss a lot of the session. As I mentioned, we are using a pre-recorded presentation from our 2020 convention. And so in the presentation, you'll see a mention about this being part of the legacy track of our 2020 convention. We decided to make this content available to other people who didn't, who weren't able to connect and with us at our convention this year. And so this is an opportunity to see that material, but also to participate. And what I mean is both of our presenters that you'll see today in the recording will be with us live to do Q&A at the end of the session. So I'll talk about that. Q&A. So the way the questions and answers will be handled, as an attendee, you're on mute and unable to speak during the presentation or even at the end. But what you can do is you should find on your little control panel a questions pane that you can click, and in that facility you can type in your question at any time to direct to our presenters. You're welcome to submit those at any time during the presentation. I'll serve as moderator and I'll be holding those until the end. Then we'll go live with our webcams on, and the presenters will have their webcams on, and we'll be able to have a little bit of dialogue with our presenters. So again, encourage you to submit questions as we go along. If there's even a slide number that you noted that you're particularly interested in, or some description of the slide, go ahead and pop that in the question as well, because then we can go back. The presenters will have their slides available to go back and cover in a little more detail if there's something you want to cover. If you're on a mobile device, iPad specifically, or any other mobile device for that matter, you should have a little question mark tab up there in your working pane, and you can click that and then be able to type in questions for the Q&A. So with that, I'm going to go ahead and get started with the video presentation. It runs about 40 minutes. That should give us about another 10 or 15 minutes to do Q&A. We do want to try to wrap up as close as we can to the top of the hour in respect of everybody's time. But if we need to run a little long because there's interest in questions, we certainly can do that. So with that, I'm going to pause and begin the presentation.
Greetings and welcome to the ASBI 2020 Virtual Convention Legacy Series with the topic of Smart Bridge Sensors on the new I-35W St. Anthony Falls Bridge, a 10-year study. Before introducing today's speakers, I would like to present the RCEP slides. To go over today's purpose and learning objectives at the end of this presentation for the I-35W Bridge, you will be able to know how many sensors were placed on the structure, gain knowledge of how actual measured creep and shrinkage movements and strains, along with the appropriate thermal gradients, compare with contemporary specifications and proposed formulations. Also understand the lessons learned from the monitoring program over 10 years, and consider those lessons for application on future projects. My name is Chris Burgess. I'm a principal bridge engineer with FIG, and co-presenting with me is Kent Montgomery, a senior project director for FIG. I would also like to thank Kevin Western, the state bridge engineer with the Minnesota Department of Transportation, for his thoughts and input. To start, I will discuss some opening remarks and a history of the program development. Then I'll move into describing the bridge, and then the design criteria that was used during design, and then also discuss sensor types and their locations. Then Kent will take over and then provide an evaluation of the results from the 10-year study, and then also some recommendations for design and some lessons learned. Now we'll move on to some opening remarks in the history of the monitoring program development. The I-35W Bridge is a major thoroughfare through downtown Minneapolis. The collapse happened on the afternoon of August 1st, 2007. The collapse destroyed the public trust. A key aspect of continuing forward is how could MnDOT replace this critical link on I-35W while communicating to the public their design build process for design and construction. Up until the time of the collapse, MnDOT has not utilized the design build project on such a large project. The RFP contained a criteria for communication. This was under the public involvement section, which was 15% of the total score. This included impacts to the public and also an approach to communication, which was extremely important. The health monitoring system was included under the public involvement proposal as a value-added item. The scoring panel thought that the health monitoring concept was outstanding, so it was developed and continued for the project. The health monitoring system ended up being a key component to help restore the public trust. The Minnesota DOT engaged with the University of Minnesota, which is nearby to the site, to assist with data collection, modeling analysis, and reporting. It should also be noted that MnDOT doubled the number of sensors that the Flatiron FIG team proposed, and in retrospect, this was a very good idea. The goals of monitoring were threefold. One was to provide construction benefits. Getting the sensors at some locations in as soon as possible allowed us to have knowledge of the structural behavior during construction. For example, we could determine concrete strengths during curing, but also temperatures during curing for mass concrete placements. Also, understanding the bridge over time, that the bridge was within its certain design parameters. This included creep and shrinkage, global thermal movements, also live loading, such as displacements for a given live loading condition, and then thermal gradients throughout the depth of the structure. Also, the important one was to restore public confidence. During design and construction, MnDOT was frequently asked about the bridge design since the project required a maximum 14-month schedule. The monitoring program was a key component in helping restore public confidence. Now I'm going to move into a description of the bridge, and then also the design criteria that was utilized, and then along with the sensor types and their locations. Here you can see a longitudinal layout of the bridge. Some key components to mention here is that it's a concrete segmental box girder bridge. The main span over the river was precast segments, and these were cast adjacent to the site with the long line casting method. The remaining spans were cast in place on false work. The 3-span unit, main unit, articulated with expansion joint at the abutment and at Pier 4, and was pinned over the main piers, Piers 2 and 3. The north abutment was integral. The unique shape for the single span at span 4 was due to crossing over some railroads. Spans 1 through 3 were 25 foot deep at the piers and 11 foot deep at the midspan and ends. Span 4 to get over those railroads was 6 foot deep at midspan. The abutments rest on driven steel piles, and the piers rest on drilled shafts socketed into rock, the main piers there, 2 and 3. There's a northbound and a southbound structure for the 3-span unit. The largest span was 504 feet over the river, and the side spans varied from 236 feet to 341 feet. Span 4 was 147 feet. In the transverse direction, each northbound and southbound alignment was 90 foot, 4 inches wide. Again, 2 parallel bridges, each with 2 sets of concrete box girders. These were connected with a small longitudinal closure strip in the center. The bridge was striped for 5 lanes in each direction. However, it was designed for 7 lanes. And it was also designed for a future configuration of 4 lanes plus a light rail or dedicated bus lane. Some relevant design criteria for the monitoring study included the following specifications. The MnDOT special provisions and design manuals were utilized. Also the AASHTO LRFD bridge design specifications. These were the 4th edition from 2007. Also the CEB FIP Model Code 1978 was utilized for concrete time-dependent properties. This integrated with the in-house BC program that was utilized for time-dependent staged analysis. For loadings, pretty basic stuff. Superstructure concrete was set to 155 pounds per cubic foot. Substructure concrete was 150 pounds per cubic foot. Live loading was the standard HL93. We did have that future allowance for light rail as well. The thermal gradients for design were from AASHTO LRFD Zone 2 with a 46 degree Fahrenheit top surface temperature. For coefficient expansion of concrete, 6 times 10 to the minus 6 per degree F was utilized. And Minnesota has some pretty extreme temperature ranges. It's very hot in the summer, but obviously very cold in the wintertime. The mean design temperature was 45 degrees F, and it has a rise of 75 degrees and a fall of 75 degrees. For material properties, the pure concrete was 28-day strength of 4,000 psi, and the superstructure concrete was 6,500 psi. Typical PT strand bars and mild reinforcement were utilized. 7-wire strand for PT, grade 270, PT bars, grade 150, and mild reinforcement at 60 KSI. The time-dependent properties, again, taken from CEB FIP 1978, we used a relative humidity of 73%, and some of the major parameters were the creep delayed modulus of elasticity was 0.4, the creep flow coefficient was 2.38 from a casting day of 0. This gave a total creep coefficient of 2.78 from casting day 0 to infinity. The shrinkage coefficient was 000223, and this also was from casting day 0 to infinity. These numbers are pretty basic for a segmental bridge. For the allowable longitudinal stresses for the superstructure, maximum compression was 0.45 F'C for dead load plus PT. Including transient loads, it was 0.6 F'C times phi sub W. Phi sub W is per AASHTO LRFD 5747. This is pretty typical for most segmental bridges. For the maximum tension, however, the top surface was set to a minus 250 psi residual compression criteria. This was unique to the I-35W bridge. To put it in comparison to a tensile criteria, that would be about 3.1 square root F prime C in psi units. Again, this was a residual compression for the top surface. For the bottom surface precast, no tension was allowed, and for the bottom surface cast in place, 3 square root F prime C at psi units was allowed. Principal tension was the basic requirement, 3.5 square root F prime C in psi units. Moving on now to sensor type and locations. Over 500 sensors were deployed throughout the bridge. 7 sensor types were utilized. These were vibrating wire strain gauges with integrated thermistors to measure temperatures. Also resistance strain gauges were added, along with fiber optic sensors, linear potentiometers at the expansion joints to measure movements, also accelerometers at various locations, and some corrosion monitoring sensors in the deck. and many standalone thermistors were also placed at various locations in the cross sections to measure temperature. Now moving on to specific sensor locations. The vibrating wire strain gauges and the resistive strain gauges, these provide strain and temperature information about the bridge's response. The vibrating wire strain gauges are located in the superstructure, and the resistive strain gauges are located in the substructure for Pier 2 for the northbound bridge. These resistive strain gauges were only utilized and monitored during construction. They were not wired for long-term use. Shown here is the location of the fiber optic sensors in light blue. These are 13-foot long strain gauges. They're placed externally inside the box and in the longitudinal direction. Not only do these measure average strains, but given the 13-foot length, they can also measure curvature and deform shapes. One item to note here is 6 locations are shown, but at each location there was a sensor placed on the top slab and on the bottom slab inside the box. So for many of these diagrams, there'll be multiple sensors at a given location. Linear potentiometers were placed in both the north and southbound structure at each of the expansion joints. These measured the longitudinal bridge movements by having a piston that could move back and forth. Accelerometers were placed at the midspans of spans 1, 2, and 3 for both the southbound and the northbound structure. However, there were also additional sensors placed within the northbound structure over the main span. The accelerometers record the structure's response to live loads and moving loads. Using data analysis, you can also extract out and estimate the vertical displacements due to these loads. Corrosion monitoring sensors were also included. These were in spans 1 and 3 for both the southbound and northbound structure, and they were embedded in the top deck. These were used to measure the potential of chloride penetration in sacrificial steel rods that protruded from the sensors themselves. Many additional thermistors were also added into the concrete at various locations. These were at spans 1, 2, and 3, and 4 midspan, and also over the piers. These were cast internally into the concrete to directly measure temperatures. Now to go in a little bit more detail where the thermistors are located. The primary concentration of them are at the midspan of span 2 on the southbound bridge and the midspan of span 2 on the northbound bridge. The circles shown here in green show the location of the thermistors, and the number nearby the circles show the number of actual thermistors at that particular location. The line through the circle shows the orientation of how those thermistors are distributed within that location. For example, at a location where there's 6 sensors, there would be one near the top, one near the bottom, and then 4 distributed kind of evenly throughout the depth of that section. For this particular study, the mid-main span and linear potentiometers at the expansion joints are what provided the most data for the study. For data acquisition, all the sensors were wired to a server shed near the bridge. Here you can see a picture of that. This shed also incorporates the anti-icing system, so it's kind of a dual purpose. There are 2 main components to data acquisition. One is static results, and the other is dynamic results. For static results, the vibrating strain gauges and fiber optic gauges and thermistors were utilized. Originally, this was set up to record data every 6 hours, but after 1 year of operation, the sampling rate was changed to every hour. This was to capture the maximum thermal gradients to make sure that was captured, since a 6-hour sampling rate was too coarse, it was found out to be. For dynamic monitoring, the accelerometers and the linear potentiometers and fiber optic gauges could be utilized. Originally, this sampling rate was at 200 hertz, but that was backed off to 100 hertz, and then the linear potentiometers were backed off further to 4 hertz. 1 year of dynamic monitoring requires about 250 gigabytes of storage. Sensor tests and calibrations were performed before the bridge was open to traffic. Live load testing was performed the late evening of Sunday, September 14, 2008. In joking, we were talking about using elephants for this test, but obviously 8 sand trucks side by side at 25 tons each would be easier to utilize. Elephants is our code word. These sand trucks were driven slowly, under 5 miles an hour across the bridge, and the sensors were monitored. They were stopped temporarily at various key locations, for instance, the mid-spans of each span. We found that the structure behavior was stiffer compared to the design. This was completely expected. The concrete strengths that were achieved out in the field were quite a bit higher than the 28-day strengths from design. Now Kent is going to provide an evaluation of the 10-year study along with recommendations for design.
And the report focused on 2 important aspects of design: creep and shrinkage behavior, which is a time-dependent behavior, and thermal gradients. So why is creep and shrinkage important for the design of segmental bridges? Creep strains typically lead to superstructure moment redistribution. Creep strains also induce column moments due to their axial shortening, and there are equilibrating superstructure moments if you have monolithic columns. Shrinkage strains, on the other hand, do not lead to significant superstructure moment redistribution. Shrinkage strains, similar to creep strains, induce column moments due to axial shortening, and there are equilibrating superstructure moments for monolithic columns. Creep and shrinkage strains are a major contributor to bearing and expansion joint movements, typically larger than the thermal movements when taken together. And overall in the design, creep strains typically dominate over shrinkage strains in their impact on the design. That is due to the fact that it leads to moment redistribution, which is very important, and also due to the fact of the amount of pre-stress that we use in our structures today. And this is an example of what we're talking about with creep moment redistribution. This happens to be for a typical balanced cantilever structure. Now, the moment diagram in red on the top are the self-weight moments at the end of construction. There's 0 at midspan, and there's very high cantilever moments. In the blue are the continuous moments, the moments you'd get if you built the whole structure on false work, dropped the false work, or if you analyzed it with any structural analysis software. Now, what's going to happen due to creep is that the moments are going to creep from the end of construction moments towards the continuous moments, but they're not going to get all the way there. And how far they get is a function of creep. That not only determines the magnitude of the positive moment at midspan, but how far that positive moment extends towards the pier. So again, this is very important for analyzing segmental structures. And this is the axial shortening effect. It's pretty easy to see as the structure shortens due to creep and shrinkage and also temperature effects that it induces forces in the substructure. So it's very important for the design of columns and foundations. In the case of monolithic columns, as we see here, there are crossover moments as shown in the bottom moment diagram, and there are, of course, then self-equilibrating moments in the superstructure. Another consideration in the design of segmental bridges is that the design is based upon 2 times in the bridge's life: into construction, when the bridge first opens to traffic, when there is minimum creep and shrinkage in the completed bridge. There is some early stage creep and shrinkage that does occur during construction, but this typically does not affect designs all that much. The second time we check the design is at long term, at the end of the bridge's design life expectancy, when there is maximum creep and shrinkage. The design for each time is a complete service and strength limit states design. By doing this, with the minimum creep and shrinkage on one side and the maximum on the other, we bracket the design, and it's easy to see that using a model that produces the maximum creep and shrinkage increases that bracketing and the reliability of our bridge. There are a lot of design formulations for creep and shrinkage, including the model codes like 1990, 2010, ACI, Ashto-Hassan equations, and Professor Bezant has proposed several models. Recently, ASBI did a study of creep and shrinkage formulations that dovetails nicely with the I-35 report. These are examples of creep coefficients from the various formulations. And you can see down here that we have AASHTO and ASBI predicting a low amount of creep compared to the other formulations. And up at the mid-height, we have the model codes 1990 and 2010. So keep those trends in mind as we look at later slides. And this is a graph of shrinkage strains from the ASBI study. And we can see here that ACI predicts a low amount of shrinkage. AASHTO and the model code 1990 predict a medium amount of shrinkage, and the model code 2010 predicts even more shrinkage. Keep in mind that shrinkage has a lesser impact on design than creep strains. So what does the I-35W monitoring report say? It compared creep and shrinkage behavior in two ways. First, by checking the longitudinal displacements in the structure, which allows you to check the axial effect of creep and shrinkage, as well as creep and shrinkage strains, which allows you to check the redistribution effect. Measured displacements and strains at various locations along the bridge and in the cross-section, then used a finite element model to calculate the same displacements and strains for several creep and shrinkage formulations. It compared the measured displacements and strains to the calculated displacements and strains. The goal was to ascertain which creep and shrinkage formulations best modeled the I-35W bridge. And this is an example graph from the report showing the displacements at Pier 3, one end of the main span structure. And we can see the graph components down here, those predicted from the ACI and the AASHTO creep formulations. Here in the blue center line is the predicted displacements from the model code 1990, and up here is the Bezant, B3, and some of the other formulations predicting even more displacement. Now in the black are the measured displacements from the structure. They're very jagged because of temperature effects, but you can see that generally they trend between ACI and 1990. And here's another example graph from the report. This is for creep and shrinkage strains in the bottom flange of midspan 2, which is a very important location. And again, we see the same trends with AASHTO and ACI predicting a minimum amount of creep and shrinkage strains. Here in the blue center line, we've got the model code 1990 and some of the other formulations studied predicting even more creep and shrinkage strains. And in this case, you can see that the measured are tracking pretty well right on top of the 1990 formulation. So what are some of the conclusions and recommendations from the I-35W monitoring report? The measured behavior was bounded by the model code 1990 and the ACI formulations. Now, ACI typically underpredicted creep and shrinkage behavior and served as a lower bound, while the model code 1990 overestimated creep and shrinkage behavior and served as an upper bound. Therefore, the model code 1990 would be best for design that is conservative and overpredicts behavior. Remember, the design is already bracketed by end of construction with minimum creep and shrinkage, and the long term with maximum model creep. So overestimating long-term creep and shrinkage produces a wider bracketing in the design and hence a more reliable design. Based on the ASBI study, the model code 2010 is also an acceptable creep and shrinkage formulation, as it has behavior similar to the model code 1990. Now we'll talk about thermal gradients. And why are thermal gradients important in the design of segmental bridges? Thermal gradients produce stresses in the cross-section, and it's primarily the tensile stresses that we're interested in. Nonlinear gradients produce self-equilibrating compatibility stresses due to the assumption of plane sections. And this is true for both indeterminate and determinate structures. Linear and nonlinear gradients produce stresses due to kinematic restraints in statically indeterminate structures. Positive thermal gradients, top fiber warmer, tend to produce tensile stresses for design in the bottom fiber. Negative thermal gradients, top fiber cooler, tend to produce tensile stresses in the design of the top fiber. The magnitude of the stress is a function of the magnitude of the gradient, of course, that makes sense, the difference between the top and bottom temperature, but also the shape of the thermal gradient is very important in determining the magnitude of the stress. Now this is a graphical representation of what we've been discussing. On the left are the internal stresses due to a nonlinear portion of the gradient. Now they occur in either a statically indeterminate or determinate structure. In the center are the external stresses to the restraints of indeterminate structures. You add the two together and you get the total stresses. Now this happens to be for a positive thermal gradient, so there's tension on the bottom. But I want to call your attention to this spike up top. For a negative thermal gradient, that spike is tensile, and the magnitude can be fairly high and requires a significant amount of extra post-tensioning to combat. Yet the extent of that spike only extends a few inches down into the cross-section. We'll talk more about this in later slides. So what does the I-35W monitoring report have to say? They compared thermal gradients in the cross-section to design thermal gradients from AASHTO and the New Zealand Code. Due to the number of thermal sensors in most sections, the magnitude of the gradients could be measured and compared. But one section, the midspan of span 2, is heavily instrumented, and the gradient shapes could also be compared. Now this was all measured. Now given the code gradients and the measured gradients, stresses were then calculated and compared to calculated stresses from the design gradients. The goal was to ascertain which design thermal gradients matched the measured I-35W bridge thermal gradients the best, and calculated stresses for measured and designed thermal gradients were also compared. This is a graphic from the report comparing the AASHTO and the New Zealand or Priestley gradients. Let's take a look at the graphic on the right as it's a zoom of the top slab. You can see a little better what's going on. Now notice both gradients have the same top temperature. It's because they've scaled the New Zealand gradient to have the same zone 2 top temperature, 46°F, as AASHTO has for bridges in Minneapolis. This is the AASHTO bilinear gradient extending 16 inches to the cross section. This curved line is the New Zealand gradient extending about 1 meter into the cross section. You can see that there's a greater area under the curve for the New Zealand gradient, so it's going to have a greater impact on the stresses in the cross section. On the left are the negative gradients. This is the bilinear AASHTO gradient, minus 0.3 of the positive. New Zealand gradient is linear, the top temperature minus 0.4 of the positive. I called your attention to what the stresses would be about 2 inches down into the cross section. Due to the shapes, they'll be quite a bit different, even though the top temperature is the same. This is a graphic from the report comparing the gradient magnitudes. I realize that both the New Zealand and the AASHTO have the same top temperature, so we're really comparing temperatures 2 inches below the surface to temperatures on the bottom. On the top, we see the positive gradients cycling throughout the year. We can also see that they regularly exceed the AASHTO gradient, while the New Zealand or Priestley gradient serves as a reasonable upper bound. On the bottom are the negative gradients. Now remember that the AASHTO has a different multiplier, minus 0.3, compared to the New Zealand gradient with minus 0.4. You see that the gradients regularly exceed the AASHTO gradient, but that the New Zealand gradient serves as a reasonable upper bound on the measured gradients. There's a few blips here and there, but all things considered, that's a reasonable upper bound. Now we'll discuss the shape of the gradients. On the right is a section that includes the top slab, the webs, and the bottom slab. On the left is a section that includes just the top slab with no webs below. Let's focus on the left section because it's at a scale where we can more easily see what's going on. We see the bilinear AASHTO gradient here and the curvilinear Priestley gradient here, both to the same top temperature. And these are the points of measured gradients at different times in the structure's life. And you can see that they're trending basically upwards towards about the same temperature. So that's a good confirmation. But we also see that these points effectively track more closely to the Priestley gradient. And as we noted before, the area under the curve greatly influences the stresses in the structure. Now let's look at the stresses that were calculated using the AASHTO and the New Zealand gradients in the report. On the left are the top fiber stresses, and we're most interested in tension, so we're interested in negative gradients. And we can see that the New Zealand gradient up here produces a little bit higher stresses than the AASHTO gradient here. On the right are the bottom fiber stresses. For bottom fiber stresses, we are interested in the positive gradient producing tension on the bottom, and we can see that the New Zealand gradient producing higher stresses than the AASHTO gradient, which is the behavior that we would expect given the shape of the gradient curves. Now let's look at the stresses computed from some of the measured gradients as compared to some of the specification gradients. Now curves were fit to various measured gradients, and then the stresses calculated the same way you would for the specification gradients. Now this graphic from the report shows stresses top and bottom both for negative gradients. On the left we see the top fiber stress, and we see the colors representing the measured gradients, and for most of the gradients they track fairly closely to the New Zealand gradient, while the AASHTO gradient predicts less stress. On the right are bottom fiber stresses, and we can see the same basic trend that for the most part, shown in the colors, the measured gradient stresses track very well with the New Zealand gradient, with the AASHTO gradient producing somewhat less stress. So what are the magnitudes of these differences in stress? For the bottom fiber at midspan 2, the New Zealand gradient versus the AASHTO gradient produces an extra 124 psi, or about 1.5 square root f prime c. For the top fiber at midspan 2, the measured gradient this time versus AASHTO produces about 130 psi extra tension, again about 1.5 square root f prime c. Now we want our designs to be as accurate as possible, so this is good information for future code adjustments. I think we realized that if we had about 1 to 2 square root f prime c extra tension in our structure that's already been designed, we wouldn't be that concerned about it. There probably wouldn't be cracking at that level of stress. So what are some of the conclusions regarding thermal gradients in the I-35W monitoring report? The measured thermal gradients are more accurately predicted by the New Zealand code proposed by Priestley. The AASHTO LRFD Zone 2 top temperature of 46 degrees Fahrenheit appears reasonable for Minnesota. The shapes are different. The multipliers for negative gradient appear more accurate for the New Zealand code, the minus 0.4 versus the minus 0.3. Interestingly enough, I went back and took a look at the AASHTO guide specifications for thermal effects of concrete bridge superstructures and found out that the AASHTO LRFD specifications don't follow exactly this document. And the AASHTO guide specification design gradients closer follow the New Zealand code and will produce higher calculated stresses than the AASHTO LRFD specifications, really somewhere in between but closer to the New Zealand code. And the AASHTO guide specifications were used for design from approximately 1990 to 1995. And why this information wasn't brought forth into the LRFD specifications, I really don't know. Now, the calculated stresses using the New Zealand code gradients most effectively capture the stresses calculated using the measured gradients. And the calculated stresses using the New Zealand code gradients and measured gradients are larger than calculated stresses using the AASHTO LRFD specifications, as we have seen from some of the previous graphs. Some additional thoughts regarding the conclusions. Thermal gradients in the bridge were measured, and a lot of good information was obtained. Stresses, on the other hand, were calculated based upon standard methods, assuming plane strain within the depth of the cross-section. It is suggested in this presentation that existing strain gauge data could be used to verify the plane strain assumption. It is further suggested that existing data could potentially be used to tease out something closer to a measured stress. Note that other research, such as this report at the University of Florida, indicates that the very steep strain gradient associated with thermal gradients has minimal influence on cracking behavior, and they concluded that self-equilibrating compatibility stresses from the nonlinear portion of the gradient can possibly be ignored for design, and that you need to utilize only the stresses due to the kinematic restraints. And this would help save a lot of post-tensioning, combating that sharp spike in tension stress that we saw. Some recommendations regarding thermal gradients. One is that additional research may be needed to determine thermal gradients for different locations across the United States. Current AASHTO LRFD specifications utilize a fairly coarse distribution oriented mostly east-west. Note that significant research does exist from the authors listed here from locations such as Minnesota, Hawaii, Texas, and California. So there's a good start to this research. It can either verify or possibly refine the current AASHTO zones. Very importantly, additional research is needed to determine thermal gradient influence on cracking behavior. At least one researcher has determined that the nonlinear portion of the gradient doesn't seem to have a great influence on cracking. There's also a lack of anecdotal evidence on cracking behavior due to negative thermal gradients. And so this would be a great addition and help us possibly save PT battling that sharp spike in stresses that we saw. And next I'll summarize the presentation and look at some lessons learned. Now, the monitoring system was the first holistic bridge monitoring done in the state of Minnesota. And approximately 90% of the originally installed sensors are working, which is a really great track record. Excellent data was obtained for the I-35W Bridge. And the knowledge adds to a better understanding of the behavior of all segmental bridges, as well as concrete box girders in general. Engaging the University of Minnesota was very important to study the large amount of data, to model the bridge behavior with different creep and shrinkage models and thermal gradients, and to provide an independent view of the information obtained. Now, some lessons learned from the monitoring system. No usable data was obtained from the corrosion monitoring system, so that should be done differently, if at all. Now, temperature readings are very important for strain gauges, and so for externally applied strain gauges, it's important to place internal thermal sensors nearby. Get absolute readings as soon as possible after installation to have a benchmark, and have researchers on site during installation and for initial readings to know the exact location of the sensors and to get the benchmark readings. For maximum thermal gradient, readings at a sampling rate of about 1 per hour should be utilized. However, a sampling rate of 1 every 6 hours should be sufficient for long-term effects. Need to consider electrical grounding and ease of power cycling, protect from electrical storms and eliminate downtime. And for thermal gradient monitoring, need to have more than one heavily instrumented section. So you need to place sensors heavily in each section that has considerable differences in section properties. Now a summary of the results. The Model Code 1990 predicts the measured creep and shrinkage behavior of the I-35W Bridge most closely. Both ACI and AASHTO underpredict the measured creep and shrinkage strains and displacements, and therefore it would be somewhat unconservative to use for design. The Model Code 1978 overpredicts the creep and shrinkage strains and displacements, and is therefore conservative. Based upon the ASBI study, the Model Code 2010 would also be a good creep and shrinkage formulation for design, has very similar behavior to the Model Code 1990, especially out of an age of about 100 years. Now, the New Zealand Code thermal gradients match the measured gradients of the I-35W Bridge most closely, and the AASHTO thermal gradients tend to produce lower stress effects than either the measured or the New Zealand gradients, primarily due to the shape of the gradient. And overall, the results from the monitoring system show that the I-35W St. Anthony Falls Bridge meets all the stress limitations set forth in the AASHTO LRFD bridge design specifications. And that is for the design, creep and shrinkage models and thermal gradients, those that were used during the design of the bridge, as well as all creep and shrinkage models and thermal gradients studied. Now, the tensile stress limitations that were used for design were zero tension for the bottom fiber and 250 psi residual compression, which is more conservative than AASHTO, but was nevertheless used for design in the top fiber. And here we see the stresses calculated for the bottom fiber, the mid span of the main span. This is the zero tension criteria here. And we can see that the total stresses, shown in solid red, are greater than 0 for all cases studied. That includes using the Model Code 1978 for creep and shrinkage and the AASHTO thermal gradient. The stresses are still above 0, as well as using the Model Code 1990 with the New Zealand or Priestley gradients as recommended. Again, the stresses are well above 0. And these are the top fiber stresses at the same location, midspan of the main span. This is the 250 psi residual compression limit. You can see that the total stresses shown here in solid red are all well above the compression limit. That includes the case of using the model code 78 with the ASBI thermal gradient as shown here, as well as the model code 1990 shown here and here versus either the measured or the New Zealand gradient. In all cases, the stresses are well above the 250 psi residual compression limit. And that concludes the presentation. We thank you for taking time to view this presentation and hope that you found it informative. If you have any questions, since this is a virtual presentation, please send them to the emails below. Kevin Western at the state of Minnesota, Chris Burgess or myself here at FIG, and we'll respond to those questions as quickly as we can. Thank you.
And actually, we're going to respond to the questions live. So I'm going to ask our presenters to turn on their cameras along with me, and we'll cover the little of the Q&A that has come in during the presentation. Thank you, gentlemen, for that presentation and also for hanging with us here. We have probably about 10 minutes or so for Q&A, and we do have a few questions that came in through the chat that I do want to cover. And the first one I will direct to Chris. It has to do with the design of the system. And that question is, does the server shed have a backup power system?
Yes, that's a very good question. There is a backup system now, I believe. When the system was first put together, there wasn't like a substantial backup system early on during the process, but during the accumulation of data, there was determined to be a need for a backup system. Power outages did affect the recording of the data. The power did go out, and then you would have to go to the shed and manually reboot and start up the system. So power management is definitely something that really needs to be considered when putting together these systems. Also, lightning strikes would have an effect on the system as well. So careful attention to lightning and power fluctuations is extremely important. Part of this is due to the fact that there's large runs of power and wires that expose the system to power surges and to lightning.
Sure.
So that was something that really needs to be considered and is now.
So then, sort of related to this, we had a question, was kind of a 2-point, which was, what was the overall additional cost of the monitoring system? I don't know if you have that number available.
That's another good question, and I do see the question that come across, and it also includes the question about seeing this technology being used on existing structures or for all structures, or just a one-off solution. As far as cost, I did discuss these particular items with Kevin Western back when we were putting together the legacy presentation. And what Kevin mentioned is that the cost of the system was substantial. I do not have an exact number. During the design build process, of course, the contractor has all the costs, and certainly wasn't shared specifically with myself. But Kevin did mention that the cost was extensive, and that makes sense because there's a lot of sensors and substantial amount of hardware. There's a separate shed that was constructed, and through that there's also kind of an additional maintenance requirement that goes past construction. You have to maintain the shed, you have to maintain the equipment in order to have it monitored properly throughout the years, and there's definitely a cost with that. With all that said, Kevin mentioned that he thought for this particular exercise that it was seen as pretty much a one-time deal to collect the data, and of course the data is useful. Kevin also mentioned that as far as future projects, he felt that such an extensive monitoring would probably not be done unless it was found to be necessary for that particular project. Here it was, because of what was mentioned, it was to help restore public confidence was a major player in having this data. But of course, 10 years from now, 10 years after the bridge being built, having this data is wonderful because then you can really see how it compares to the design.
Right. So, well, thank you. So the next question that came up was I'll direct to Kent, which was, are there any differences in thermal gradients between precast structures and those that are cast in place?
And the answer is, as far as the specifications go, there is no difference. The behavior is identical as far as the calculations. There are obviously some differences, and that would be a small thin epoxy joint that I really don't believe would affect the thermal transfer all that much, considering the sun or the open night sky is what's driving the heat transfer from the top downward into the section. There's been various structures that have been instrumented, and no one has determined a difference between precast and cast in place, and intuition tells me it would be very small, if even there at all.
Okay. Another question, and I think you kind of covered this in your presentation, and that the question was, did the monitored movements come close to calculated movements, thermal, et cetera, during design?
And is it possible to bring up slide 38?
We will hop over and see if Chris can do that for us.
Yeah, to share my screen. Can you see the slide, the intro slide?
See the intro slide. See if we get the right slide at 38.
It'll get you there.
You should see it now.
Okay, these movements at Pier 3 as an example. And you can see the various creep and shrinkage formulations. I think this is what we're talking about, the movements. And for design, we use the model code CEB 1978, which is this purple line on the top. We did so for two reasons. One is we chose to use a structural analysis software, BC, that it easily accommodates that, but not so easily accommodates some of the other formulations. And also because we knew it was conservative, and you can see that here. So if you project it out, you're seeing that you're getting about an inch, maybe a little more of extra movement predicted than what we're seeing, which is good. You got a little bit extra movement capacity in your joints and bearings. You can also see with the blue line right above the measured, the 1990 model code. And in that case, they're getting pretty close, although the blue is giving us maybe an extra ½ inch of movement. And so you can see that using the model code 1990, or as we've seen from some of the other studies, the model code 2010, are going to give you pretty accurate movements, but a little bit on the conservative side, which is good.
So then, while I got you, another question related to this: was the instrumentation able to discern the difference between creep and shrinkage effects, or are they looked at together as a whole?
They had to be looked at together as a whole. I mean, we just have either potentiometers or strain gauges, and they're just measuring the total movement or strain. You can obviously tease the temperature out of them because you have the thermistors at the same time, but to my knowledge, I don't see how you would differentiate between creep and shrinkage.
Right. So then in Chris's portion of the presentation, he mentioned that the data obtained from the corrosion sensors ended up not being useful. Can you talk a little bit about that?
Yeah, the corrosion sensors, I guess, from the very beginning failed, and no data was obtained from them. The cause of that failure, I do not know off the top of my head, and I think in the report it didn't specifically mention the cause, and I don't think it was understood or found. So the system as it was, the corrosion monitoring system did not work as planned. So that was unfortunate in that regard. But
Right.
since I have the floor, I just wanted to add another few bullet points to the discussion we had previously, and it's in regards to maybe the future with regards to monitoring. During the I-35W, I mean, there was a lot of design that went in, custom design, custom data acquisition systems, custom hardware. For the future, maybe to bring the cost down and complexity down, I think we can certainly take advantage of the technology. Certainly, probably more plug and play components now exist compared to back then. Cloud storage could be utilized and maybe decrease the amount of maintenance and physical machine monitoring and placement on site. That's something that's getting more use these days. Also, wireless technology certainly can play a role as the future goes on here to help reduce the long power line runs and the long wire runs, which would maybe perhaps reduce the exposure due to power fluctuations and lightning. So I just wanted to bring that out while I was thinking about it, that while it was kind of mentioned that maybe you don't want to go to this extent on all projects due to cost and maintenance, if it arises to where the technology catches up to where it makes that cost greatly reduced, it may make sense to start instrumenting more common projects.
Right. And there was another question sort of tied to that, which was for how valuable the info was. Do you see ASBI or AASHTO commissioning these installations on other projects in the future to refine their requirements? And I'll speak on behalf of ASBI. As an institute, we're not really a research institute, but certainly we work frequently with Federal Highway and other research institutions to develop problem statements. And certainly this is an area we're interested in taking, as Kent mentioned, gathering data on some other structures. And in fact, some of it already sort of exists in a body of data that a lot of that could be mined without really having to do a lot of additional instrumentation, although more data is always better, and we certainly would be supportive of that. I don't know if you had anything you wanted to add, either of y'all, on that one.
Well, I certainly agree. As a designer, having this data from I-35W and having the feedback, as much cost as it took to produce it and as much maintenance that was needed during the 10 years and it continues is very valuable. Having the feedback just alone on the long-term creep and shrinkage that's displayed on the slide here is incredible, because normally you design a bridge and you build it and you have a particular creep and shrinkage assumption, and then it's just understood from past experience that it's conservative, and there's other tests and such that have shown that, but at least here you can really see it throughout a discrete pattern that's continuous. Of course, there's little blips here and there, but you can really see that it's following the same shape, but it's conservative from the design, and it's close to the 1990. I mean, that's very valuable information, as hard as it was to obtain. So as a designer, I like having the information, but certainly understand the cost and the effort it takes to get it.
So in that vein, there was another question, says, I know we installed instrumentation in the drilled shafts. Is this data recorded in the same facility, and have you looked at that data?
The data in the drilled shafts was only utilized during construction. The data is not included in the 10-year study report. If memory serves, that data is included in the construction documents. That data was used to monitor during the construction of the bridge for concrete strength, and also we looked at its strains and such as we were loading the bridge to make sure that that was in the established parameters, which it was. But that data has not been recorded for long-term use, and it's not recorded now.
Right. Okay. And so somewhat related to this, and this might be more one for MnDOT, and that is this monitoring system being used in conjunction with the normal biannual field inspections?
That's a good question, and Kevin Western or MnDOT would have to answer that one.
Okay, so I will follow up on that question with MnDOT, and we're going to we'll be posting the Q&A here and answering any of the questions that we didn't quite have time to answer during this. I did want to give Kent Montgomery an opportunity. Kent is the chair of the ASBI Design Committee, and he's been working very closely with AASHTO committee lately. He made reference to earlier in his presentation to a creep study that ASBI did, and I wanted to share that. So that creep study has been shared with AASHTO T10 for consideration of perhaps a minor revision to the AASHTO provisions on creep and shrinkage, just to put it within those boundaries. But I'm gonna let Ken, if you want to talk about that. Obviously, it's a pending issue. That is, it's up before AASHTO to sort of decide how to move forward.
Yes, this sort of dovetails into the question that Chris answered about having data, and it's a very good thing and very timely. As you're aware, in the last 5 or 6 years, there's been some questions regarding creep and shrinkage brought up by some various engineers and professors. And so having this data is very timely in showing that the models that we've been using for design are adequate and slightly conservative. So this is extremely good data. Now, what was brought up in the ASBI study, and if you could put up slide 35, Chris. And we saw this on the previous slide too, but you can see that down low in the amount of predicted creep are both the AASHTO and the ACI formulations. And then at mid-height in purple and orange are the 1990 and 2010 formulations. And the 78 is way up high, although that's formulation works a little differently. So let's just concentrate on the difference between AASHTO, ACI, and the model codes 1990 and 2010. The way the LRFD specifications are written right now, you would be following the specification if you used ACI or AASHTO for your creep and shrinkage predictions. Yet we saw on this graph, as well as some of the MnDOT data, that would be under predicting the creep and shrinkage. And so there is currently a working agenda item, 216A, that will be voted on this year. That is basically going to direct designers of segmental bridges to use the model codes 1990 and 2010. And so that there's no chance to under-design due to creep and shrinkage. Now, to my knowledge, most experienced segmental designers have been using the model code, so I don't believe there's issues out there with existing bridges. As we move on, of course, 1990 is getting outdated, even 2010 is in a way, but we want to start shifting towards the 2010 code. 2 reasons. One is it's just more current, but the other is if you look at the detail of what's going on in this graph between the orange, which is the 2010 code, or sorry, the orange, which is the 1990 code, and the purple, which is 2010. Now, for this case here of 70% relative humidity, at about 100 years out, they're going to give you the same amount of creep and shrinkage. It was just that or in this case, creep, the model code 1990 just gets there a lot faster. And since we bracket the design, you'll get the same answer and the same design about 100 years out. But as we strive to make our structures more durable and have a longer service life, you can see that the 1990 code has become asymptotic to a maximum value, while the 2010 code continues to show a smaller and smaller amount of long-term creep that we want to capture if the bridge life is much longer than 100 years. Hopefully that's probably more than what anyone wanted to know about it, but does that answer the question?
Yeah, that covers it, Kent. Thank you. So we did have one final question, and I know we run a little bit past time, but folks are still online, and I don't want to cut folks off. I want to make sure we answer as many questions as we can. Last question then will be on the longitudinal displacement graph, what happened at day 100, 500, 1,000, and 2,000?
I believe you're probably talking to the gaps in the data there. And again, that would be slide 38, I believe. And I believe that is just simply when we lost data acquisition to power glitches and stuff.
Gotcha.
And so we had to pick it up a little bit later. Is that your understanding, Chris?
Yes, absolutely, that's correct. There were times where data was not collected due to the system being down. They had to rewire it, or went through a lightning strike and it was down for a few months or a few days. So there's little areas that where data has not been recorded.
So, and then there's a spike at day 100. Oh yeah, there's a little.
That's a good question.
I really don't know what went on there, to tell you the truth. Sometimes early on in data acquisition, you know, in the early days, you just get these anomalous spikes, and just through observation, I would just throw it out as a data anomaly.
Right.
It might have been a lightning strike or something, but the power was still on, and the filtering software didn't catch it. But
right.
Yeah, hard to say. I don't remember it being specifically mentioned in the report. It might have been. Obviously, it's an anomaly.
Right. All right. Well, thank you, gentlemen. With that, we're going to wrap up because we have run a little bit past time, and I want to respect everybody's time. Maybe next webinar we'll schedule a few more minutes for Q&A. I will follow up with MnDOT on the one question, and then also any other questions that come in. If you have any questions afterwards, certainly shoot those to me by email. You can do that. Let me hop over here. I think next slide. Yeah, here's a reminder on if you have any questions, you can either submit it to me at gfreebie@ASBI, or you can send it to the info@ASBI. Either way, it'll get to us. And then one last reminder, if you're not already following ASBI on LinkedIn, I would encourage you to do so. You'll see we're getting very active in using social media, not only to showcase upcoming webinars and events, but also looking back at some of our past projects and what's going on in the segmental bridge building industry. So it's sort of a great place to pop in and see kind of what's the latest and what's going on. So again, thank you to our presenters, Kent Montgomery and Chris. We appreciate Burgess. We appreciate both of y'all putting together this presentation from our convention, and also then for hosting us today in a webinar. One last reminder, again, we're doing webinar April 28th. You can register for that one. It's already up on the website. I encourage you to go ahead and register for that. And with that, we'll sign off, and I'll see you at the end of April.
Thanks, Greg.
Thank you, everyone.
Thanks.